So the first problem is y equals 3x plus x squared cubed. And we're just going to try to figure out the derivative for this. So this is a chain rule problem. What's the outside function? X to the third, good. And Connor, what's the inside function? Awesome. So we're doing good with that. So when we take the derivative, you do the derivative of the outside first. The outside is x cubed, so the derivative of that is 3x squared. So there's the first step of the chain rule. Take the derivative of the outside. Then the second step is plug the regular inside into it. And then the third step is multiply by the derivative of the inside. So that's 3 plus 2x. And remember, you're gonna be fine with this, because really all you're doing is bringing the 3 out front and subtracting 1 from it, right? So visually, that's easy to do. That's eventually what you're going to do in your head instead of coming through the 2 steps. So 3 out front, subtract 1, but then you'll accidentally forget to multiply by the derivative of the inside. So just watch out for that. Okay, so that was nothing new, just to kind of get us going here. So how about we have r equals the square root of the tangent of 5 theta. So the first thing that sometimes throws people off on this problem is the variables are different. But don't let that throw you off. The theta is like the x, and the r is like the y. So we just have x and y. They're just different variables. Still have input and output. And so when you get the derivative, instead of dy dx, it would be dr d theta. But it's still the same meaning. Dy dx is the derivative. So in this case, the variables are r and theta. So the derivative is going to be dr d theta. Okay, so now looking at this, what's the outside function? The square root, good. And that's the 1/2 power, right? Is there another perspective on what the outside function is? Yeah.
So is that 3 functions? Or is that 3 different ones? Because you have the square root, then the tangent, and then 5 theta.
So Colin's saying there's 3 different functions here. There's 5 theta on the very inside. There's tangent of 5 theta on the inside of the square root. And then there's square root. So one perspective is that square root is the outside function. And that's the very outside, I agree. And then another perspective is tangent is the outside function, because 5 theta is inside of tangent. Okay, so this is a new type of problem that has 3 functions in it. The 5 theta is the very inside, and the square root is the very outside. Okay, so just like yesterday, you work from what's happening last in. So remember when we try to decide between product rule and chain rule, when the multiplication was happening last, that was dominant. So here, the square root is happening last, so that's dominant. Okay, so the outside function is the 1/2 power. So you take the derivative of that, and it's 1/2 blank to the negative 1/2. If we're treating square root as the outside function, then that means that tangent of 5 theta is the inside function. So that's what's going on here. So when we plug the regular inside into it, what we're plugging in is the tangent of 5 theta. So there's where we are so far. That's the first 2 steps. Take the derivative of the outside and then plug the regular inside into it. Okay, then the last step is to multiply by the derivative of the inside. But I'm deciding not to think about that right now, so I'm just writing it down. I'm just saying hey, don't forget we have to multiply by the derivative of the inside function. Okay, so I haven't done this yet. I'm just saying, let's do it in the next step. Okay, so then, when we take that derivative, that's another chain rule. Because this is 5 theta sitting inside of tangent. So as we work our way down, we're going to have to do a second chain rule. Okay, so for this function, what's the outside function? Tangent, good. And so the derivative of that is secant squared. And then we have to plug the regular inside into that. If tangent is the outside function that we're thinking about, then 5 theta is the inside function. So we plug the regular inside into it. And then you multiply by the derivative of the inside, which would be 5. Because the derivative of 5x is 5. So the derivative of 5 theta is 5. And I like to put it in front so there's no confusion about what's being multiplied by 5. So now I'm going to recopy the rest of this. Okay, so here's the real reason why the chain rule is called the chain rule. Because you have this times this times this. And so it just keeps getting, there's a big chain of things multiplied in a row. So the reason we have 3 things multiplied is because this was 3 functions. It was 5 theta inside of tangent, inside of square root. That's about as far as the chain's going to go for us, a 3 chain. But it's possible there could be, this could be to the 7th power, and then that could be signed, and so then it would keep going and going. But don't stress out about that. Most of the time it's just going to be 3 for us at most. But I at least wanted to show you that so you could see where the chain rule got its name. That times that times that is a big chain of stuff. Okay, so that was double chain rule because it had 3 functions. Here's one that sometimes throws people. Y equals the secant of 5x. So what's the inside function? 5x, right? And the outside function is secant. So the first step is to take the derivative of secant. So maybe you don't have that memorized yet, but what is the derivative of secant? Secant times tangent. And the thing that's kind of weird about secant times tangent is there's 2 blanks in that function, right? It's the derivative of secant x is secant x tangent x. So there's 2 different blanks. So here's the derivative of the outside function. Then when you plug the inside into it, the 5x goes in both of those places. So that's the thing that throws people off sometimes. In step 2, there's 2 places to put the 5x. And that's just because secant x tangent x has 2 different x's. And that means it has 2 different places where the input goes. Okay, so that was the first 2 steps of the chain rule. And then the last step is multiplied by the derivative of the inside. The derivative of 5x is 5. So I just multiply by 5. And normally we put that at the beginning to avoid confusion at the end. Yeah?
We're both secant tangent multiplied by 5.
When you have a string of 3 things multiplied in a row, you don't distribute. So if it's plus, then yeah. But if it's multiplication, then no. You just either do the 3 times the 4 or the 3 times the 2. So that's what's going on here. Now I can see how maybe in the chain rule you were thinking that the 5 would go with both of them. No, it's just times a 5 at the end. Good. how about y equals sine cubed of x times tangent of 4x. Okay, so is this going to be chain rule? Yeah. Why? Where's the chain happening? Where's the composition? Tangent of 4x, right? Okay. What else is going to happen here? Product rule, because there's a time sign here. Okay, so then we have to decide, is this a dominant product rule or a dominant chain rule? And it's a dominant product rule because this multiplication is happening last. So if you had a number for x, you'd multiply it by 4, and then you'd take the tangent, and you'd get a number there. And then you'd also take the sine of the number, and then cube the answer, and that would give you a number there. And then the last thing you would do is that number times that number. So since the multiplication is happening last, it's dominant product rule. Okay, so you have to take the derivative of the first thing, and I don't want to think about that right now, so I'm just going to write it down. The derivative of the first thing. So normally when I do product rule, during this step, I actually figure out the derivative of the first thing and write it down. But I'm delaying that, and I'm saying, hey, just remember, I'm going to have to do that derivative. So that's the derivative of the first thing times the regular second thing. And then plus derivative of the second thing, which I'm going to delay till later. Times regular first thing. So the reason I'm delaying is I just wanted to think about product rule in that step. I didn't want to mess, since maybe I'm kind of tired, stayed up late last night, I didn't want to think about chain rule during that step. I just thought derivative of the first times regular second plus derivative of the second times regular first. And now for the next step, I'm going to concentrate on figuring out the chain rule problems. Okay, so you told me this was a chain rule because it was 4x sitting inside of tangent. So the derivative of that, so I'm working after my plus here, right? The derivative of that would be secant squared of 4x times 4. So I'm getting a little more casual now and just slapping down the answer without talking about it too much. Does everybody agree that this is the derivative of tangent of 4x? Okay, so then I times that by sine cubed. And then for this slot, I have to figure out the derivative of sine cubed. The best way to think about that is to rewrite sine cubed. Sine cubed is this, right? So this means exactly the same thing as sine cubed. So to figure out that derivative, I just do 3 sine of x squared. So maybe you would be more comfortable if I wrote that down. But that's the same thing, right? Okay, then what else? Multiply by the derivative of the inside, right? And the inside is sine. And the derivative of that is cosine. So I'm going to run out of room here. That's okay. So before I go on, is everybody comfortable with all of that being the derivative of sine cubed? That big long string of things is just the derivative of sine cubed. Okay, so then to finish things out, I have to recopy this tangent 4x, right? So I did this part first, so it messes up. So let me write it a little neater. It's 3 sine squared x cosine of x, tangent of 4x plus 4 secant squared 4x times sine cubed of x for the final answer. Fun, fun, fun. So people are feeling okay about chain rule. Okay. Because some years people don't like it at all, but it seems like this year it's going fairly well. But ask me a question if you need help. Even if you feel like everybody else in the room knows what's going on, remember, I'll be impressed if you show some guts and say, wait a second. Okay. So next we got example 5, which makes sense because that's after 4. So they're going to give us some information in example 5. It's a table. So this is just a table of information, kind of like one on one of the homework problems. So what this is saying is, if you plug 3 into g of x, the answer is negative 4. And if you plug 3 into f prime, the answer is 2 pi, et cetera, et cetera. So it's just giving you some values for different functions at the value x equals 3. And we're just going to use those to answer some questions. Okay, so the first one is, okay, so before I write down the question, I want to write the directions like they are in the book because they confuse people a little bit. So what it says is evaluate the derivatives of each of the following functions. At x equals 3. Evaluate the derivatives of each of the following functions at x equals 3. And the first function is f of x minus g of x. Okay, so I'm not going to plug 3 into this function because the directions didn't say evaluate the following functions at x equals 3. It says evaluate the derivative of this at 3. So what I have to do first, before I plug 3 in, is I have to take the derivative of this. Okay, but if I take the derivative of 2 things subtracted, how does derivative behave with 2 things subtracted? It just goes past the subtraction sign, right? So you can take the derivative of the first thing minus the derivative of the second thing. So that's easy. Okay, so when you see problems like this, what I would like to see you, as far as showing work is concerned, I want to see the derivative of the function first, before you plug the number in. Because that's how derivatives work, right? You can't plug the number in and then take the derivative. You have to figure out the formula and then plug the number in to figure out the specific value. So same thing here. Okay, so now I'm going to put 3 into this. Because it said evaluate the following derivatives at 3. And so to figure out f prime of 3, I just read that off the table. That's 2 pi. And g prime of 3 is 5. And so the answer is just 2 pi minus 5. Okay, so subtraction is easy with derivatives, right? We know that. But division is tougher, right? So if I was going to take this derivative, since there's division, I have to use quotient rule. So you take the derivative of the top times the regular bottom minus the derivative of the bottom times the regular top all over the bottom squared. Okay, so subtraction with derivatives is a piece of cake because you can just distribute derivative past subtraction. But division with derivatives is tougher because you can't just take the derivative of the top and the derivative of the bottom and divide them. You have to use quotient rule to figure out the correct derivative. So now here's my formula for the derivative, and now I can plug 3 into that. So f prime at 3 is 2 pi. And g of 3 is -4. And then g prime of 3 is 5. And f of 3 is 3. And g of 3 is -4. So I know maybe some of you could write this down first, but on the homework I want to see this just to show your work. And the reason why is when you take a derivative, you have to find the formula before you plug the number in. So some of you can think through that, but it shows more understanding if I see both of those steps. So I've learned over the years that if I make people write this down, they're more successful 2 months from now with stuff that's going on. So, okay, so 2 pi times -4 is -8 pi. And then 5 times 3 is 15. And -4 squared is +16. And then that's enough. All right, next function is g of f of x. Okay, so part A was easy because it was subtraction, right? Part B was a little tougher because it was quotient rule, but not too bad. We're getting pretty decent with that now. It's been going on for a few days, maybe a week. What kind of rule is this? Yeah, it's a chain rule. It looks like multiplication, right? Because the g is right now next to the f of x, but it's not multiplication because it's f of x plugged into g. So this is a composition. So this is chain rule. Okay, so what's the outside function? G, right? And F's inside. Okay, so what's the first step for the chain rule? Derivative of the outside. Okay, so in this problem, G is the outside, so we take the derivative of that. And that's just called G prime. Okay, so then what's the second step for the chain rule? Plug something into that, right? And you plug the regular inside into that. The regular inside in this case is f of x. So there's the regular inside plugged into G prime. So now we're done with the first two steps. And the last step is to multiply by the derivative of the inside. So there's my formula for my derivative. Notice this looks a lot like what I wrote down yesterday. Remember yesterday I said, hey, to take the derivative of f of g of x, you just take f prime of g of x times g prime of x. And I tried to get you to understand that, but it was a Wednesday, and so you weren't quite there yet at the end of the day yesterday. But now it's clicking a little better, right? Because that's the outside. So this is the derivative of the outside with the regular inside plugged into it times the derivative of the inside. So same thing, except the roles of G and F are switched over there, right? Because G is outside and F is inside on this problem. So that's why I keep saying outside and inside rather than F and G, because it's really arbitrary what the functions are called. The real concept is there's the outside one and then there's the inside one. Okay, so I don't think I really had time to emphasize this. This is the chain rule. So go back to your notes from yesterday and just do that. Draw an arrow to this and say, hey, that's the chain rule. Now for you guys, the three-step process that I wrote out in English is the chain rule. And that's fine. But this is the chain rule spoken in the math language. So it's still the chain rule. So to mathematicians, we don't use words to speak. We just use these symbols to speak. And then eventually you get sophisticated enough, and these symbols mean the same thing as the words. So this is the chain rule written in the mathematical language. So that's what the last example yesterday was about, trying to get you used to this language rather than the three-word language that I had written out. Okay, so anyway, here's the derivative for letter C. So now I have to plug 3 into it, right? So I have to plug 3 into that function. So I'm going to figure out f prime of 3, and that's 2 pi. Just reading that off the chart. Then I'm going to figure out f of 3. That's 3. Okay, now here's where people are going to go wrong. They're going to find g prime of 3, right? And they're going to put a -4 there. And the reason they're tempted to do that is because this looks like multiplication, right? You see how the g prime is right next to the f? So this appears to be multiplication. But this is not multiplication. This is this plugged into g prime. Are you with me? If there was an x there, g prime of x times f of 3, that would be multiplication. That's not what's going on here. This is this number plugged into g prime, because that's what the chain rule says to do. Take the regular inside and plug it into g prime. So I've got to take this value that I get and put it into g prime. That's very subtle, what's going on right now. Is everybody okay? And the reason it's tough is because somebody made a bad decision at some point to have next to mean multiplication in some contexts and composition in other contexts. I mean, there's English words that happens, right? You have the same word means two different things depending on the surrounding sentence. That's what's going on here. This juxtaposition, this next to, means multiplication in some context, but here it means composition. Okay, so then you plug 3 into G prime, and that comes out to 5. And then 5 times 2 pi is 10 pi. All right. All right, I got one last question for you. So the question is the derivative of sine of x the same, regardless of whether you are in radians or degrees? So in order to get to the bottom of this, I'm going to graph sine of x and look at the slope of the graph. Okay, so when you're in radians, you go pi over 2, there's like 4 marks, right? And you do pi over 2, and pi, and 3 pi over 2, and 2 pi. And I think everybody probably has a vague recollection that sine goes back and forth between 1 and -1, right? It's the wave. What's hard to remember is, does sine start here or does it start up there? Sine starts at 0. It's cosine that starts up there at 1. Okay, so sine of x starts there, and then it goes up to 1 at pi over 2, and then it goes down to pi at pi, sorry, down to 0 at pi, and then down to -1 at 3 pi over 2, and then finally back to 2 pi, back to 0 at 2 pi. So one cycle of the wave looks like this. So that's a graph of sine of x. Okay, so I'm going to look at the, oh, and it cycles back this way too, right? So I'm going to look at the slope of sine at 0, because I'm trying to figure out what's going on with the derivative of sine. Since the question asks what's the derivative of sine, that's why I'm looking at the slope. So I'm just going to draw in, and this is not an exact science, I'm just drawing in a tangent line at 0. So let's see here. It's a pretty decent tangent line. I'm just trying to draw a line that represents how steep this graph is at 0. Okay, so pi over 2, again, this I'm not being exact here. Pi is about 3, so 3 divided by 2 is about 1.5. So down to the bottom there, I'm going to reference that that's about 1.5. And so 1 is about right there. If that's 1.5, then 1 would be 2/3 of the way there. Okay, so then if I look at this slope, it looks to me like it's kind of going up 1 over 1. So I'm estimating that the slope at 0 is 1. It turns out the slope at 0 is exactly 1. Because I know the derivative of sine is cosine, right? And the cosine of 0 is 1. So I pretended like I was eyeballing, but I went ahead and was accurate just so there'd be less confusion. Okay, so now let's change to degrees. Okay, if we're in degrees, what is that? 90 degrees, right? Pi over 2 is the same as 90 degrees. So then that makes this 60 degrees, because it's 2/3 of the way to 90. So now the graph is going up 1 over 60. Let me say that again. Look, it's going up 1 and then over 60. So if we're in degrees, the slope at 0 is about 1/60th. That's a lot different. 1/60th is tiny compared to 1. So is the derivative of sine of x the same regardless of whether you are in radians or degrees? That answer is definitely no. Okay, so that means that all of those trig derivatives that I told you 2 days ago, 3.5, when I said the derivative of sine was cosine, and the derivative of tangent was secant squared, all 6 of those, they're only true if you're in radians. Let me say that again. They're only true if you're in radians. So now you know why they worked so hard to get you used to radians. Like you thought, why? 90 degrees is so much easier than pi over 2. I agree. But the real reason that pi over 2 is better for our purposes is because the derivative of sine is cosine, a nice, simple formula. Whereas if you're in radians, it's a much more complicated formula that's harder to memorize. Okay, so now all that work about radians that you did from the past is paying off. Okay, so the pain is sort of for a reason. So that's why in calculus you're always in radians. And actually, that's sort of awkward for those of you who are in physics right now, because in physics class you're in degrees often, right? So what I'm going to invent someday is a force field there that as you pass through the force field, it changes your calculator into radians, just in case you were in physics before you came. It's still in the developmental stages. I don't have it yet, but it would be really cool. But what I'm saying is mentally, when you come in this room, you got to be in radians, because calculus is always in radians. All right, is everybody good? Thanks for listening.